Have you ever watched a basketball soar through the air and wondered how it reaches its target? Or marveled at the arc of a perfectly thrown football? These captivating feats of athleticism and countless other everyday occurrences are governed by a fascinating principle of physics known as projectile motion. Understanding this concept allows us to predict and explain the motion of objects flying through the air, from the mundane to the extraordinary. Whether you're an athlete aiming for that game-winning shot or an engineer designing the next generation of spacecraft, grasping projectile motion is key. At its core, projectile motion describes the curved path an object takes when launched into the air. Think of a baseball being hit or a cannon firing a ball. These projectiles, once launched, are influenced primarily by Earth's gravity and their initial launch conditions. By understanding the interplay of these forces, we can accurately predict where a projectile will land, how long it will remain airborne, and even its velocity at any given moment. This predictive power is what makes projectile motion such a crucial concept in fields ranging from sports and ballistics to engineering and space exploration. But it's not just about hitting targets or launching rockets. The beauty of projectile motion lies in its elegance and ubiquity. It's at play every time a drop of rain falls from the sky, every time you jump in the air, and even in the graceful arc of a fountain spray. Recognizing these everyday examples of projectile motion allows us to appreciate the underlying physics that govern our world. So, the next time you see an object flying through the air, remember that you're witnessing a fundamental principle of physics in action, a principle that has captivated scientists and stargazers for centuries. One of the key players in the drama of projectile motion is gravity, that invisible force that keeps us grounded and dictates the motion of objects around us. In the context of projectile motion, gravity acts as a constant downward force, pulling the projectile towards the Earth's center. It's this relentless pull that gives projectile motion its characteristic curved path. Without gravity, a projectile would simply continue in a straight line, never returning to the ground. Imagine throwing a ball horizontally. If there were no gravity, the ball would continue traveling horizontally at a constant speed forever. However, we know this isn't what happens. Instead, the ball's path curves downwards, eventually hitting the ground. This downward curve is entirely due to gravity, which constantly pulls the ball towards the Earth. No matter how fast you throw the ball horizontally, gravity will always be there, acting independently of the horizontal motion. This independence of horizontal and vertical motion is a crucial concept in understanding projectile motion. Gravity only affects the vertical motion of a projectile, pulling it downwards. It has no impact on the projectile's horizontal speed. This means we can separate the two motions and analyze them independently. The horizontal motion will be governed by the initial horizontal velocity, while the vertical motion will be influenced by both the initial vertical velocity and the constant downward acceleration due to gravity. The combination of constant horizontal motion and accelerating vertical motion due to gravity creates the characteristic curved path of a projectile. This path, often resembling a parabola, is a testament to the interplay between these forces. The steeper the launch angle of the projectile, the higher it will go and the longer it will stay in the air. Conversely, a shallower launch angle will result in a shorter flight time and a shorter horizontal distance covered. Let's visualize this with an example. Imagine two archers aiming at targets equidistant from them. One archer aims their arrow at a steep angle, while the other aims at a shallower angle. Which arrow will reach the target first? The arrow launched at a shallower angle will hit the target first, even though it travels a longer horizontal distance. This is because the shallower launch angle imparts more of the initial velocity into the horizontal component, allowing the arrow to cover the ground more quickly. The shape of the parabolic path is also influenced by the initial velocity of the projectile. A projectile launched with a higher initial velocity will travel farther and reach a greater height than one launched with a lower initial velocity, even if they are launched at the same angle. This is because a higher initial velocity means the projectile has more energy to overcome the downward pull of gravity. Understanding how launch angle and initial velocity affect a projectile's trajectory is crucial in many applications, from sports to warfare to space exploration. By precisely controlling these factors, we can accurately predict and control the path of projectiles, enabling us to achieve specific goals, whether it's hitting a target, launching a satellite, or landing a rover on Mars.